Welcome to the 28th lecture on Advanced Steel Design course. We are in the process of deriving the stability functions. Now, in this lecture we will continue to learn the rotation coefficients. And then the stiffness matrix of a standard beam. Let us rewind back. This is what we discussed in the last lecture. We learnt how to obtain KRP and KSP in terms of PP and QP with reference to figure 1 and figure 2. Let us focus on figure 3 now. Friends, the standard beam looks like this. Okay. So, if I give a unit rotation of theta p as unity, this invokes a moment which is KPP and KQP, is it not? If this is true, then suppose if I have a beam where the rotation is 1 by Li, where this is L. So, this is figure A. Let us have one more figure and the kth end. If I give a rotation here, then this gives me a moment of KQQ and KPQ, is it not? So, this is equivalent to a member where I give unit displacement here and the member rotates by 1 by L. Okay. Now, considering these two figures and comparing this with figure 3 and 4, let us say KPR is a moment which is invoked by giving unit displacement at the rth end. But can I write KPR as an effect of these two sum for unit rotation? So, I am writing KPR as KPP plus KPQ into 1 by L. Why 1 by L? KPP and KPQ are the moments for unit rotation, whereas KPR is the moment for 1 by L rotation. So, I am multiplying this with 1 by L. Okay. So, I can write KPR, is it not? Similarly, can I also write KQR? Similarly, KQR can also be a sum of KQP plus KQQ by L, because again these are moments because of unit rotation. But I want moment because of 1 by L. So, therefore, I can multiply this with 1 by L. Okay. So, therefore, friends, once in this figure I know KPR and KQR, let me copy this. And I will put it here. So, I already know KPR as KPP plus KPQ by L, is it not? See here. I also know KQR as KPQ plus KQQ by L. See here, KQP, right, by L. Okay. So, now I can write the net moment here is KPR plus KQR, which is here. So, now I can say KRR is actually KPR plus KQR by L, because that is a couple. Can I now write KRR as KPP plus KPQ plus KQP plus KQQ by L square? Okay. So, now can I also write KSR as minus of KRR, because that is a couple. So, this will be acting downward, this will act upward, this becomes a couple. To counteract this moment. Okay. Similarly, let us do this for the other end. Let us copy this figure and put it here and we will work on this. Similarly, same order I am just trying to do for the other end. You know, KPS will be actually KPP plus KPQ by L. KQS will be KQP plus KQQ by L, but there is a small change here. Originally KPP, look at here, originally KPP, okay, and KPQP were anti-clockwise, is it not? But I am here looking for a clockwise moment. So, shall I say these two are minus? Is it not? They are opposite to the original one, is it not? So, if I know the net moment is KPS plus KQS, then this will have a moment which is a couple like this, is it not? So, this is going to be KRS, going to be KSS. So, I can now write KRS as KPP plus KPQ plus KQP plus KQQ by L square, but with the minus sign, whereas KSS will be KPP plus KPQ plus QP plus QQ by L square, but with a plus sign, because this sign matches with this. So, now I have all the coefficients. Let me transfer these coefficients to the matrix. So, what is the original matrix K? The original matrix K is, if this is P, if this is Q, R and S, this is P, Q, R and S are the labels. So, this is KPP, KPQ, KPR, KPS, KQP, KQQ, KQR, KQS, KRP, KRQ, KRR, KRS, KSP, SQ, SR, SS, isn't that? So, now I have all the values with me. Please look at your notes. They have all the values. Let me write down these coefficients here. I will tell you a very simple way to remember this. Okay, it is a very simple way. The K matrix can be easily remembered. Please watch here. So, it is easy for you to recollect. So, it is a 4 by 4 matrix. Please watch here. P, Q, R and S. P, Q, R and S are the labels, right. This is KPP and this is KQP. This is KPQ, this is KQQ. And this value is KPP plus KQP by L. It is nothing but sum of these two by L, and this is minus of this. Similarly, sum of these two by L will be here. This is minus of this. The third column is very easy. Sum of these two by L. Second element, sum of these two by L. Third element, sum of these two further by L. So, that becomes KPP, KQP, K. KPQ, KQP, QQ by L square, isn't it? And this will be negative of this, minus of PP, PQ, QP, QQ by L square. Now, once you written the third column, the fourth column is very easy. The fourth column is minus of third column. So, minus of KPP, KQP by L, minus of KQP, KQQ by L, minus of PP, PQ, QP, QQ by L square, then plus of KPP, PQ, QP, QQ by L square. Friends, you can always note that the elements along leading diagonal or positive. Okay, they are positive, they can never be negative. So, please check that when you do the derivation and understand it very carefully. So, in this matrix, these 4 values 1, 2, 3 and 4, these are called rotation coefficients. Let us say this is my matrix. This P, Q, R and S are the degrees of freedom. These are called rotational coefficients, and these 4 are called translational coefficients. Friends, carefully look at the derivation back. Look here, in this equation, if you know this value and this value or these 4, okay, I can fill up the remaining matrix very fast, is it not? So, I need to know only the rotational coefficients. If I know the rotational coefficients, I can fill up this matrix very fast. So, our job is to now derive the rotational coefficients. Okay. So, the rotational coefficients will be derived based on the flexibility method. Okay. So, we want to consider a simply supported beam. Okay, as shown in the figure. So, I will draw the figure. Let us consider a simply supported beam. Okay, we will consider 2 figures. In one figure, we will give unit rotation at jth end. This is my jth end, this is my kth end, is it not? We will give unit rotation. So, I am going to now use flexibility coefficients. I know flexibility and stiffness are inversely proportional, we know that. So, I will find the flexibility coefficient matrix and invert it to get the stiffness matrix, which is rotational matrix. To do that, I want to give, let us say, unit rotation. Okay. So, let me give a unit rotation here. So, let us say I give theta j is unity. Okay. So, I draw a tangent to this, I call this as del jj and I call this as del kj, where these are flexibility coefficients. Okay. Similarly, I give unit rotation at the kth end and I call this as del kk and I call this as del jk. Okay? So, now imagine we will compare this. Okay, I will copy this. I will compare this with our standard member which is initially normal and this is KPP, we know that, and this was KQP and this was theta p, which is unity. I am comparing these two figures. Similarly, an equivalent figure for this would be comparison of, we can even draw this straight. Theta q is unity and this was KQQ and this was KPQ. Am I right? And these are equivalent. Okay. Now, comparing these two figures, I can write the control equation like this: del Jj, del Jk, del Kj, del Kk, which are flexibility coefficients, multiplied by Kpp, Pq, Qqp, Qq will give me identity matrix. There is a 1:1 match, okay, 1:1 match, give me an identity matrix. So, this is my flexibility matrix, this is my stiffness matrix, my identity matrix. Okay. Now, my question is to find these values of flexibility matrix. If I know this, I can invert this matrix to get my rotational coefficient matrix. You see here, this is what I want. This is what I want. This is KPP, this is KPQ, this is KQP, this is KQQ. This is what I want. This is here. So, to get this, I will first find the flexibility matrix and invert it, I will get this matrix. Okay. To get that, flexibility is inverse of stiffness. Let us define what is stiffness first. Kij is force in ith degree for unit displacement in the kth degree by keeping all other degrees of freedom restrained. Now, I want to write the flexibility definition. Flexibility coefficient will be displacement in ith degree for unit force in kth degree by keeping all other degrees of freedom restrained. Is it not? Just the reverse of this. So, displacements can be of two: rotational, translational. If I give a rotational displacement, I will get a moment. If I give a translation displacement, I get a force. Okay? So, now I must give unit rotation at ith degree. I mean, I have to find the rotation at ith degree by giving unit moment at the kth degree. Okay, that is what I am going to do now. Let us do that. So, let me draw the figure of the simply supported beam again. Is having length L. This is my displaced configuration. I want to give unit moment. Okay. And the displacement cost is rotation, which is del Jj, and here this is del Kj. So, let me draw the bending moment diagram of this. So, I have given unit moment here and this is 0. So, by this logic, tension will be at the top and compression will be at the bottom, is it not? I have given moment like anti-clockwise here, right. So, let me apply this as an M by EI diagram to my beam. So, this is my conjugate beam. I am loading this beam with my M by EI diagram. This is my M by EI diagram. Okay. That is how this diagram is done, is it not? Right. So, this is going to be 1 by EI. Why 1? Because this is actually unity. That is what is here. Right. So, this will have a CG somewhere here. This will be at the distance L by 3. Okay. Now, this will invoke reaction here and here, let us see. We call this as VB, this as VA. Okay. Now, let us take moment about A. So, half into base into height, that gives the area of this triangle, into the distance of the CG from A, which is L by 3, should be equal to VB into L, provided VB is now opposite. Okay. So, I can now find VB as, so L goes away, so it is going to be L by 6A, am I right? It is acting downward. Okay. Now, I can say VA will be equal to half into base into height, the total force, minus L by 6 EI, that is what my VA is. So, this will give me VA as L by 3 EI acting upward. So, this is L by 3 EI, this is L by 6 EI. This is acting downward, this is acting upward. So, I have VA and I have VB. Okay. Now, as per the conjugate beam effect, these will be the displacements. Okay, these will be the displacements. So, I can straight away say they are going to be, I can write here, this is going to be del Jj and this is going to be del Kj. I can do the same way for the other end. Similarly, one can do this process at kth end Okay. So, if you do that, you will get the same equation. If you do that, which we already drew. Let me copy this. Let me copy this figure. Let me rub this. Okay, if you do that, you will find that we wanted to find del kk and del jk. Del jk will be minus 6 L by 6 EI and this will be L by 3 EI. So, we have now all the 4 values. We have del Jj as L by 3I, del Kj as L by 6EI, then del Jk as minus L by 6EI and del Kk as L by 3A. I can write this in a matrix form as L by 3EI minus L by 6EI minus L by 6EI and L by 3EI. This is my flexibility matrix. I want to find the stiffness matrix of rotational coefficients, which will be inverse of this matrix. So, that will be KPP, KPQ, KQP, KQQ, which will be, you can take inverse of this, which is L by 3 AI minus L by 6 AI minus L by 6 AI and L by 3 AI inverse. You will find this matrix as 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L. So, the rotational coefficients can be obtained like this. Let us go back to the original matrix. So, we are talking about the rotational coefficients, which are these 4. if I know these 4, see KPP, PQ is what we have just found out. Okay. So, let me say if I know this, I can write the remaining. Let us see how. Let us copy this. I want the full stiffness matrix. Okay. Let us rub the remaining all. Let us see how do we fill up this. We know this. Okay. Let us rub this. This is 4EI by L. And this is 2EI by L. And this is 2EI by L. And this is 4EI by L. Just now we computed that. See here? Just now we computed that. Okay? Once you know this, sum of these two by L is 6EI by L square minus of this. Similarly, sum of these two by L, 6EI by L square, then minus of this. Then sum of these two by L, sum of these two by L, then sum of these two by L, then minus of that. The last column is negative of the third column. Okay, that is how we have the stiffness matrix of the beam element is ready. Okay. So, friends, in this lecture we learnt how to derive the rotational coefficients of stiffness matrix. We also learned how to formulate the complete stiffness matrix neglecting axial deformation. And we learned that K is 4 by 4 is very easy to write. If you know this label P, Q, R and S, if I know this value, I can keep on writing the remaining all very easily based on this. Okay. So, in the next lecture, we are going to continue discussing stability functions and axial compression, but based on the same derivation technique what we used for a fixed beam. Okay. So, keep on revising what we discussed in the previous lectures, that will be very helpful for you, and the reference already slated for you. Please go through the additional references given in the website of this course and improve your additional learning skills in parallel, so that the derivation becomes very clear for you. Okay? Thank you very much and have a good day. Bye.